Today we're talking about thiols and ethers. Thiols and ethers. Again, remember, emphasizing that this is elementary organic. Right? So the way that you talk about reactions and stuff like that in full organic is going to be slightly different, so just bear that in mind. So let's talk about a thiol first. The thiol contains the SH functional group, right? Thiols contain SH. So they are analogous to alcohols in some ways, but they're very different from alcohols in other ways. Right? Alcohols contain OH, whereas thiols contain SH, right? And if you look at the periodic table, you're looking at our periodic table, and you remember your rules for electronegativity, right? Electronegativity decreases down a group, right? Remember that from intro chem or general chem, electronegativity. In other words, how well an atom shares electrons in a covalent bond, that decreases down a group. So that means sulfur is less electronegative than oxygen is, right? So that's going to have a role in the physical properties of the thiols versus alcohols. In terms of thiols, they're smelly, okay? Things that don't smell good, a lot of times can be attributed to thiols. This is a figure from your textbook, right? Onions, oysters, garlic, those are all things that don't usually smell so great, right? And we can attribute them, a lot of their stinkiness, to the thiols. So let's talk about IMFs, right? Alcohols and amines are capable of hydrogen bonding, right? Because alcohols have OH, yes, and amines have NH or NH2, depending on if it's secondary or primary, or just plain old N, right? Those guys are all capable of hydrogen bonding. Now, sulfur is less electronegative than oxygen, and it's less electronegative than nitrogen, right? So in other words, sulfur hydrogen bond is not as polar as an OH bond or an NH bond, right? So sulfur is not hogging those electrons as strongly as OH would be hogging them, or the N would be hogging them. So that means that it doesn't have hydrogen bonding. It's polar, but it's not polar enough to be considered hydrogen bonding. So we call it dipole-dipole. So which one of these is stronger in terms of IMFs, hydrogen bonding or dipole-dipole? Hydrogen bonding is stronger, right? So that's why thiols are going to have lower boiling points than alcohols and amines, okay, if they're of the same size. If we're comparing a 10-carbon chain versus a 50-carbon chain, that's not comparable, right, because the London forces in the 50-carbon chain are significantly stronger than in the 10. But if they're of similar chain length, right, one's a 5-chain, the other's a 5-carbon chain, 5-carbon chain, and the only difference is one's got an alcohol and one's got a thiol, the thiol have the lower boiling point, right, because dipole-dipole is a weaker intermolecular force than hydrogen bonding is. So I know we don't know how to name alcohol and thiols yet, but I'm just going to sketch the structure just to make the point. Marker. So butane would be 4 carbons long, 1, 2, 3, 4. 2 butane thiol would be this. Butane, 1, 2, 3, 4, and 2 butanol, 1, 2, 3, 4. We already know how to name alcohols. Okay, right? This part, what are the IMFs here? London and what? And dipole-dipole. And this one is London only, right? And this one is London. Anything else? Hydrogen bonding, right? And these are all comparable because they're all 4-carbon chains, right? So rank in order of boiling point. I didn't say increasing or decreasing. Let's just say in order of increasing, because I didn't specify there. So who's going to have the lowest boiling point? All right, this is the lowest. Number 1, right, that's lowest. And then the thiol or the alcohol? The thiol, right? This will be number 2. And the jump between here and here is going to be big, right? That's going to be a big jump. I don't know the boiling point off the top of my head. So this will be 2nd. And then this one will be the highest. And again, the jump between here and here is going to be pretty significant too. Okay, so these are not going to be like you know, 77, 78, 79. It's going to be big gaps between them because we've got significantly different intermolecular forces going on here. So dipole-dipole is the strongest IMF in a thiol, whereas hydrogen bonding was the strongest IMF we saw in alcohols and amines. So when we name thiols, it's similar to naming alcohols. Your parent chain has to include that functional group, otherwise it wouldn't work. Your naming would not make sense, right? You want to give the thiol the lowest number if there are other substituents, right? You want to give the thiol the priority of, say, a methyl group. Always put your substituents first, and then the ending, the suffix is just thiol. And then, of course, state where that thiol is with a number. All right, so let's just do these together. So our longest parent chain needs to contain the thiol, right? 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5, 6, 7, 8, right? So we're going to go horizontally, right? We're not going to do this. That doesn't make sense. And we're going to number from the left or from the right? From the right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, what kind of substituent is this? That's ethyl. And this is just bromo. So we would name this what? 4-bromo, right? Because you still have to go in alphabetical order. Then 3-ethyl. Then what? Well, we need the 2, right? 2-octane thiol. So I'm going to pause it and let you try the next one. Oops, without showing the answer. All right, let's see if you got the second one. We did the first one together. Let's see if we get the second one. Where's carbon number 1? Left or right? Left. Is this carbon number 1? No, that's the thiol, right? This is carbon number 1. So 1, 2, 3, 4, 5, 6. A lot of students will call this carbon number 1, but that's not a carbon, right? That's sulfur. So we've got 2 substituents. Where are they? On what carbons? 2 and 3. So this would be 2, 3, dichloro, 1. Right. You just dump the word thiol on the end. Okay? Just dump the word thiol on the end. Now I want to show you in a minute another acceptable way to name thiols. So let's first do a couple more practices. Actually, move this down. Remember, I've got some more practice for you to do. So I'm going to pause it. You can't read that. Pause it and let you try this one. Draw the structure for 2-methyl-2-pentane thiol. All right, let's look at this one. So this is a pentane. So 1, 2, 3, 4, 5, 2-methyl, and it's also 2-pentane, right? So there's the methyl and then there's the pentane. I mean, there's the methyl and there's the thiol. They're both on carbon 2, right? 2-methyl-2-pentane thiol. Do we agree on this one? I think I've got one more for you to try. Yep. 3,3-dichloro, 4-methyl-cyclohexane thiol. All right, now when we have it in a ring, which functional group, well, there's only one functional group in here, right? Because the chlorine and methyl aren't functional groups. So there's only one functional group that we're dealing with, right? And so it's going to be what default number? Number 1, right? So cyclohexane would be a 6-membered ring. And then The thiol is going to be number 1 by default. That's our functional group. So we're going in reference to it. So 3,3-dichloro. So 1, 2, 3, 3,3-dichloro, 4-methyl. Got a little carried away there. Do we agree on this one? Do we get the same answer? All right. Okay, when you've got 2 thiol groups on your molecule, it's called a dithiol, okay? And you would need to state where both thiols are, right? Because you technically could have them both on carbon 1, right? It could be 1,1 ethane dithiol, or it could be 1,2 ethane dithiol, right? So you've got to state where they both are. This one would be 1,4, right? Or it could be 1,2, or it could be 2,2, right? You have to state where they are, and then the suffix just becomes dithiol. Just don't forget to state where they are. And then if there were any substituents, right? If we had a chlorine on carbon 1, it would be 1-chloro, right? Well, actually, carbon 1's over here. 1-chloro, right? Any substituents would go first. So I'll pause it and let you try these. All right, let's go over these. So we've got some substituents to deal with here. Oh, I can't write on that. I'm just gonna have to move it down further. Yeah, there we go. Okay, so where are we numbering, from the left or from the right? We're numbering from the right because we want to give priority to the thiols. So is this a number? Is this a carbon? Nope, this is where the carbon chain begins, right? 1, 2, 3, 4, 5, 6, 7, 8. All right, so we've got some substituents to deal with here, right? Which substituent comes first alphabetically? The chloro, right? So it would be 6-chloro. Then what? 4-methyl. Then what?
1, 2.
This is 8 carbons long, so right, octane dithiol. All right, in the second one, we're numbering from the left or from the right? Right, because this will get us my first functional group first, right? 1, 2, 3, 4, 5, 6, right? Because that's not a carbon, that's chlorine. So you can't count that as carbon number 1. So what's the name of this one?
1,1 dichloro.
Yep.
2, 3.
Oops, not 2-3, 2, 3.
Hexane dichloro.
All right, good. So we have to put our substituents first and alphabetical order if we have more than one substituent, and then we state the locations of our thiols. Feeling good about these? All right. I've got a couple more to try. Yep. This time, I want you to draw something for me. Five bromo 4,4,5 trimethyl 1,3 heptane dithiol. I'll pause the recording. All right, let's go over this one. Hep 7 carbon chain, right? So 1, 2, 3, 4, 5, 6, 7, and this is 5 bromo. 1, 2, 3, 1, 2, 3, 4, 5 bromo. 4, 4, 5 trimethyl. 1, 2, 3, 4, 4, 5 trimethyl, and then 1, 3, 1, 2, 3 heptane dithiol. Do we agree? And then I've got one last one for you to do before we look at another acceptable format for naming these. So try this one, 2,5-diethyl 1,3-cyclopentane dithiol. All right, let's look at this one. So this is cyclo, right? So that tells me it's a ring. And so we have pentane, 1, 2, 3, 4, 5. And we've got 1, 3. So let's do our functional group first. 1, 3. And then 2, 5. So here's 2. 1, 2, 3, 4, 5. There we go. When we were naming, right, we went this direction and not this direction. If I gave you this molecule and asked you to name it, why do you name this? Why do you number this direction and not this direction?
To give your thiols the smallest.
Right, to give priority to the thiol over the ethyl group. Good. All right, let's look at another acceptable way of naming thiols. I want to show you both formats because, again, one is what your textbook goes with, but one is a little more used commonly, I guess is a better way to talk about it. And I think your homework should accept both. So let's look at this molecule on the left here. All right. We just called this 2-hexane thiol, right? That's the naming that we just used. We said dump the word thiol on the end, say 2-hexane thiol, right? That's the way your book names thiols. Your textbook just calls it 2-hexane thiol. There you go. But we also could call it hexane 2-thiol for this one on the left, okay? Right? Splitting it up, just like when we did alcohols and amines and everything else, right? You could call it hexane 2-thiol. Your book does not use this format. Your book uses this format, but this is acceptable as well. And then looking at the molecule on the right, how does our book use it? How does our book name it? Our book would name this. We numbered 1, 2, 3, 4, 5, 6, 7, right? 4,4-dimethyl 3-heptane thiol. That's how your book would name it. But you also could have named it 4,4-dimethyl heptane, then 3-thiol. Okay? So I just want to show you both versions, right? Again, this is the version your book uses, but just so you've seen it split up like that, it's acceptable to name it both ways. And here are a couple more examples. All right, how would our book name a dithiol, right? This is what our book would call this, right? 1, 2, 3, so 3-bromo, 2,4-heptane dithiol. That's the way our book would do it. But if you're looking at other textbooks, especially when you get to Organic 1, you might, and you probably will, see it more split up like this, right? So 3-bromoheptane 2,4-dithiol. So in other words, you're moving the 2,4 into right here. Okay? So when you're doing your online homework, it should accept either one. I don't think it's going to mark you wrong if you go this way or if you go this way. This is the way our textbook does it. But just know you could put that 2,4 right there. And then with this one, this is a trithiol, right? We're numbering 1, 2, 3, 4. So we could have 3-bromo, 2,3,4-heptane trithiol, right? That's how our book would name it. But you could take that 2, 3, 4 and smash it right here in the middle. 3-bromoheptane 2, 3, 4 trithiol. Okay, so I will accept either version on the test. I'll accept either version. Like I said, homework should accept either version as well. Okay, questions on this? I'm looking at it both ways. All right, so let's just practice some naming. I'll pause the video and let you try it. Give me both acceptable names. Okay, now I wouldn't ask you for both on the test, but just for practice. Right? You could name this 4-methyl 1,2-cyclohexane dithiol, right? That's what our book would use. How would we change this to give the other version?
1, 2 after hexane.
Right. You just relocate it. 4-methyl cyclohexane 1,2-dithiol. Right? Now on a test, I wouldn't ask you for both. Just know that they are both acceptable. And then the last one, before we move on to ethers, we're going to look at ethers today too. I'll pause the recording. Let you try this one. Oops. All right, let's look at this one. So there are 3 SHs here, right? So this is a trithiol, and we need to number to give priority to the thiols. So where's carbon number 1? On the left, right. So we would say 4-methyl, right? Because we're numbering 1, 2, 3, 4, right? 4-methyl 1, 2, 3 cyclohexane trithiol. Left off the I right there. Or 4-methyl cyclohexane. Then take this 1, 2, 3 and dump it right there. Now left off the I. Thiol. There we go. Okay. Now I lied when we say we're doing ethers next. We want to talk for like 4 seconds about disulfides. This is something that will come back to us when we get to the biochem half of this class. Sulfur-sulfur bonds are called disulfides. We're going to look at this specifically when we get into proteins. So we're not going to do a whole lot with disulfides right now. I just want to introduce it so that when we do get to proteins in the biochem half, you've seen this before. All right. So R is the rest of the chain, and then there's your sulfur-sulfur bond, and then there's R is the rest of the chain again. So in other words, you've got 2 chains or 2 rings or whatever that are attached by a sulfur-sulfur bond. We call that a disulfide. It's also known as a sulfide bridge. That's all that we're going to look at right now. So here's an example, right? When we do proteins and we do amino acids, the amino acid cysteine has an SH on the end. It's got a thiol on the end. And so if you've got 2 cysteines near each other, they will form a sulfide bridge, right? You oxidize it, you get that sulfide bridge. You reduce it, you get your 2 cysteines back. So again, this will come back to us when we get into the the biochem half of this course. You'll see those sulfur-sulfur bonds when we're looking at proteins. So here's, for instance, the structure of insulin. There are 2 main chains, and they're held together by sulfide bridge here and a sulfide bridge here, and then there's kind of a little pinch in the purple chain from the sulfide bridge. So again, this will come back into the picture when we get to the biochem half, and that's really all we're going to do with this right now. All right, now let's look at ethers. Ether is just a plain old O, right? So there's something on this side, and then there's O, and then there's whatever's on this side. Okay, so that's what an ether looks like. That's the functional group ether. Now, in terms of intermolecular forces, let's just compare everything to what we've talked about already. We know alcohols and amines are capable of hydrogen bonding. They're the strongest ones on this list. Thiols are weaker, and ethers are even weaker than thiols. Now, you might say to yourself, well, hey, oxygen's really electronegative. What gives? Well, this is not an oxygen-hydrogen bond like in an alcohol, right? In an alcohol, you've got an OH. There's a big electronegativity difference between the O and the H. But in the ether, you don't get that OH. It's just a plain old O. So it's weak dipole-dipole. So if we were comparing thiols and ethers of comparable size, 4-carbon chain, 4-carbon chain, the thiol would have the higher boiling point than the ether of comparable size. Okay, so the ether will boil lower than the thiol will because the ether's got weaker dipole-dipole than the thiol does. And then all of them are going to boil way less than the alcohols and amines. But all of them are going to boil higher than the alkanes. So if we're doing these, ranking them in order, I didn't put increasing or decreasing again. Just for fun this time, let's make this one decreasing boiling point. Decreasing. So if they're going in decreasing boiling point, which one goes first? The one with the highest boiling point, right? So this is the highest boiling point, 2-butanol, right? That's highest. 1, 2, 3, 4. There's 2-butanol. 2-butane thiol we just drew a minute ago. There's butane. And then there's diethyl ether. We haven't learned how to name yet, but it's 4-carbon chain, essentially. So here's the highest. Who's next in line?
Butane thiol.
All right, the thiol will be next. Second highest. And there's going to be a big jump here, right? This is not like 1 degree difference. It's going to be a big jump because this one is hydrogen bonding and London, right? Whereas this one is what? Right, this is London plus dipole-dipole. All right, now we're trying to choose the third. Who's third in line? The ether, right? So this is third highest. And again, it's a big jump. It's a big jump between here and here. So what are the IMFs here? This is London and what else? It's weak dipole-dipole, right? Make sure you emphasize that it's weak. Those are wimpy dipole-dipole. And then here, this is going to be lowest, right? And actually these two, there's not going to be a big jump here. There's not going to be a huge jump here. This is just London only. Because London only versus London and weak dipole-dipole, that's not going to be a big difference. And I think the next slide actually has some data on there. So pretty close, but still separatable pretty easily. Right? All of these are pretty easily separated. Big jump, big jump. So make sure that you know that these ethers have weak dipole-dipole. It's not the same as the dipole-dipole in a thiol. The thiol dipole-dipole greatly exceeds that of the ether. Yeah, here's some data. Right, so here's butane. Here is methoxyethane. And then here's propanol. Right, look at the jump here. Like I said, these two are pretty close. I mean, 7.9 versus -0.5. It's not a humongous jump. It's not like they're 1 degree apart either. But then go from here to here, 7.9 to 97, right? That's a huge jump, right? Alcohol, weak dipole-dipole, just London. And then ethers, in terms of their solubility, they can dissolve in water unless that chain gets too long, right? There's no hydrogen bonding, so this ether isn't capable of hydrogen bonding, but it is polar enough to dissolve, so long as this chain isn't too long. Okay, so don't let that chain get too long, but otherwise they can be soluble. And then we can make ethers a lot of ways. The only method your textbook really talks about is by dehydrating an alcohol at a really low temperature. Now, when you take organic chem, full semester organic, like organic 1 and organic 2, you'll talk about other ways to make ethers, okay? But in elementary organic, the only version of how do you make an ether that your textbook looks at is dehydrating an alcohol, right? We talked about dehydrating an alcohol, making an alkene, but if you do it at a really low temperature, you can make an ether. I'm not going to put that as one of your required reactions, just something to know. But once you get to organic 1 and 2, you'll look at how do you make an ether in great detail. Now, when we name ether, I'm going to show you 2 ways. The first way is kind of ambiguous, so that I want to show you both versions, okay? Because one of them is specific and one of them is ambiguous. So the way your textbook names ethers, again, we're looking at how do we name ethers in elementary organic. The way your textbook names ethers is just name the side groups and then put the word ether. So for instance, your textbook would call that a methyl, right? Looking on the left, methyl. And then there's a 3-carbon chain on the right, propyl. So your textbook would call this methyl propyl ether. You see how that works?
So you don't need numbers since it's just one.
You're naming it in reference to the O. Yes. Now that's why this is ambiguous, because you would not technically, this is not IUPAC nomenclature, okay? It's ambiguous, and I'll show you why it starts getting ambiguous in a couple minutes. But you've already pointed that out. There are no numbers, right? You're not naming in reference to a chain. You're naming in reference to an oxygen atom. But this is the way your textbook presents it, and I'm pretty sure if you entered that on the homework, it wouldn't mark you wrong, because this is the way your textbook presents it. But it is ambiguous, right? Because you're not naming in reference to a parent chain. You're naming in reference to an oxygen atom. So that is why essentially this becomes ambiguous quickly. Now, if both chains are the same length, this would actually be considered the IUPAC name if both the chains are the same. Right? This is a 2-carbon, this is a 2-carbon. You could call this diethyl ether, and you could pick up a bottle back in the stockroom and it will say diethyl ether on it, right? Because you've got a ethyl group and an ethyl group. And again, we are technically ambiguous in this nomenclature, but we're not at the same time, because it's two of the exact same thing. But I mean, I've got bottles back in the stockroom that say diethyl ether on it. Now, again, your book uses this format, methylpropyl ether, but here is the technically correct name. The correct name is to look at this. You look at the two sides, and you say, okay, which side is bigger? Obviously, this side's bigger, right? 1, 2, 3 versus 1. So we're going to consider this OCH3, we're going to consider this a substituent on this. And so that's why the name is 1-methoxypropane, because this is a meth, right? And then the oxy refers to the fact that it's an ether. And it's on carbon number 1 of the propane. So this is the technical name, 1-methoxypropane. This has no ambiguity in it whatsoever, right? Because you've got a propane, and on carbon number 1, you've got an O with a methyl group. But again, your textbook calls it this, methylpropyl ether. And when you do this on your homework, it shouldn't mark you wrong. I don't think it will. But that becomes ambiguous. This is the technical IUPAC name. Okay? Now let's look at another example. If I gave you this and said, all right, name it, your textbook would call it, like that's a 2-carbon chain, that's a 3-carbon chain, ethylpropyl ether, right? But that is not the IUPAC name, right? What's the IUPAC name? The IUPAC name is to pick the bigger piece and think of this as a substituent on that bigger piece, right? So propane is the longer chain. This is a substituent, right? And it's a 2-carbon chain this time. So it is ethoxy, and it's on carbon number 1, so it'd be 1-ethoxypropane. Okay, but I will accept either version of nomenclature on tests, and your online homework should accept both as well. So that's the way those figures came directly from your textbook. So I'll give you a second to try these. All right, let's look at these. So, if we're naming it according to how our textbook would name it, we've got a 1, 2, 3. So your book would call this what? Propyl. And then 1, 2, 3, 4, 5. Pentyl, right? So your book would call it pentylpropyl ether. But let's also name it using the IUPAC rules. What would the correct name be? This is really considered a substituent. What's it called? It's a 1, 2, 3 carbon chain with an O, so it'd be proboxy, right? So this would be 1-proboxy pentane, right? I'll accept either one. And then down here, 1, 2, 3, 4, 5, 6, 7. So this is a 7 would be heptyl, right? And then 1, 2, 3, 4 would be butyl. So your textbook would call this what? Butyl, heptyl, ether. Because your textbook isn't using this oxy nomenclature. It does in rings, but it doesn't in linear. But the technical name for this would be not butyl, but butoxy, right? 1 butoxy heptane. That's IUPAC. Do we agree on these two? Your online homework should accept both as well. And if it doesn't, just send me an email. We'll figure it out. But usually, it accepts both. All right. So let's just do these together. Propoxypentane, butoxyheptane. Oh, I just did those. Never mind. Okay, now when we puts it in when you go into a ring, your textbook doesn't fool around anymore with ambiguous names anymore because it becomes too difficult. So your textbook uses IUPAC nomenclature for rings because your textbook says, well, it's now too hard to name it using what we just talked about, the ambiguous naming. It becomes way too difficult to do that anymore. So now the textbook switches over to IUPAC and says, all right, this is the bigger piece and this is just a substituent, right? So this is 1, 2, so this is ethoxy cyclohexane, right? So your textbook does switch over to IUPAC once they get out of the linear stuff. So if we were naming these, what would this substituent be called? Methoxy, so this would be methoxy cyclopentane, right, methoxy cyclopentane. And then here, what would this be? Butoxy cyclobutane, right? All right, I think we can skip those because I think we've kind of covered it. This is something we'll get into when you take full organic, but we don't spend a lot of time talking about. When you've got an ether that's replacing a carbon atom, okay, we call those heterocyclics. You're not going to have to worry about naming these in elementary organic, but get ready to see them when you take organic 1 and organic 2. So I just want to introduce it so you've seen them before. It's not something that we're going to worry about in terms of naming in elementary organic. And this is something that I already said about boiling point, solubility. Just in terms of some quick little history, diethyl ether was actually the first general anesthetic. So if you're a medically inclined person, you like learning about your history of anesthesia, that was the first anesthetic, but it's actually bad for your neurology. So it can build up in your brain and build up in your nerve cells. And so now ether still can be used as anesthetics, but notice they're highly substituted, right? All of the hydrogens have been replaced with halogens. And so that's where we're going to stop for today.